Hello dear students, all of you welcome to Vidyan classes. It is the 11th lecture on function and the second lecture on binary operation. Today we will discuss important memory tips in lecture number 10 and problem discussion on binary operation. First, important memory tips in lecture number 10. Let star be a binary operation on a non-empty set capital A. Let star be a binary operation on a non-empty set capital A. First, commutative. A binary operation star on capital A, where capital A is a non-empty set. A binary operation star on A is said to be commutative if A star B is equal to B star A. For all A and B belongs to capital A. In lecture number 10, we have discussed commutative, associative, existence of identity and existence of inverse of an element in A. Now, we will memorize these definitions. Second point, it is the definition of a commutative. A binary operation star on A is said to be commutative if this condition is satisfied. Associative. A binary operation star on A is said to be associative if A star B bracket star C is equal to A star bracket B star C. For all A and B and C belongs to capital A. For all ABC belongs to capital A, if this condition is satisfied, then star is said to be associative. Third definition, Existence of identity element in existence of identity element in A. The set capital A is said to have an identity element. The set A is said to be an identity element. The set A is said to have an identity element if there exists a unique, that means one and only one, one and only one. A unique means one and only one. If there exists a unique, that means one and only one element E belongs to A, so that A star E is equal to A, which is equal to E star A. For all A belongs to capital A. Existence of a commutative, associative and existence of identity element in A. The set A is said to have an identity element if there exists a unique, that means one and only one element E belongs to A, so that A star E is equal to A, which is same as E star A for all A belongs to capital A. If this condition is satisfied, then E is called the one and only one identity element in capital A. Existence of identity element in capital A. It is the definition. If A star E is equal to A, which is same as E star A, for all A belongs to capital A, then E is called the identity element, which is one and only one in capital A. Existence of identity element in capital A is called the identity element, where E is called the identity element where E is called the identity element in A with respect to binary operation, star, where E is called the identity element in A with respect to binary operation star. If this condition is satisfied, then E is called the one and only one identity element in A. Fourth, it is the definition of a commutative, it is the definition of associative, it is the definition of existence of identity element in A. Existence of of inverse. Existence of inverse of an element. Existence of inverse of an element in A. What is the definition of existence of inverse of an element? Existence of inverse of an element in A. What is the definition? If E is the identity element, if E is the identity element in A with respect to binary operation, star, then an element, A belongs to capital A. If E is the identity element in A with respect to binary operation star, then an element that is small a belongs to A is said to have an inverse element A belongs to A is said to have an inverse element B belongs to A such that A star B is equal to E, which is the same as B star A, or A star A inverse is equal to E, which is equal to A inverse star A star B is equal to E, which is same as B star A, or A star A inverse is equal to E, which is same as A inverse A, where B is called the inverse of A. B is called the inverse of A, denoted by A inverse. That means A to the minus 1. B is same as A to the minus 1. If this condition is satisfied, then B is called the inverse of A. If E is the identity element in A with respect to binary operation star, then an element A belongs to A is said to have an inverse element B belongs to A, so that A star B is equal to E, which is same as B star A, or A star A inverse is equal to E, which is same as A star A inverse star A, where B is called the inverse of A, denoted by A inverse, or A to the minus 1 is called the inverse of A. These are the four definitions helps to solve the problems on binary operation. We have discussed these four definitions in lecture number 10. First commutative, then associative, existence of identity element in A, and existence of an element. Existence of inverse of an element in A. These are four important definitions to solve the problems of binary operation. Clear? Clear? Okay, note down. Next, elements of mathematics, page number 30, exercise 1C. Question number 4. Construct the composition table or multiplication table for the binary operation star defined on set of 0, 1, 2, 3, 4 by A star B is equal to A into B modulo 5. Find the identity element if any. Also find the inverse element of 2 and 4. Construct the composition table or multiplication table for the binary operation star. Most important problem for CHSE. Solution. The binary operation star defined on this by A star B is equal to A into B modulo 5. Star is a binary operation. The binary operation star defined on set of 0, 1, 2, 3 and 4 by A star B is equal to A into B mod 5. What is the meaning of A into B modulo 5? A into B, A star B is equal to A into B mod 5. A into B mod 5. What is the meaning of this? It implies remainder, that is R, obtained. Remainder obtained dividing A into B by mod 5. A into B modulo 5 represent remainder obtained dividing A into B by modulo 5. Note, in the previous class we have discussed the division of algorithm. By the division of algorithm for two integers A and B belongs to set of integers, there exist two integers U and R, so that so that first condition A is equal to BQ plus R. Second condition R greater than equal to 0 less than mod of B. If these two conditions are satisfied, then the division is true. When B divides A, B divides A, gives the quotient Q, A minus BQ is equal to R. R is the remainder. When B divides A, gives the quotient Q and R. AB and QR are the integers. For example, 5 divides 0, gives the quotient 0 and the remainder is 0. 5 divides, suppose 4, the quotient is 0 and the remainder R is equal to 4 greater than 0. The remainder is always greater than 0 or equal to 0 and always less than mod of B. Mod of B means 5. 5 divides 5, the quotient is 1 and the remainder is 0. 5 divides 8, the quotient is 1 and the remainder R is equal to 3 greater than 0. Remainder is always greater than or equal to 0. 5 divides 12, the quotient is 2 and the remainder R is equal to 2 greater than 0. 5 divides 16 gives the remainder is 1 greater than 0. 5 divides minus 16 gives the remainder R is equal to 4 greater than 0. If these two conditions are set, minus 16 is equal to 5 into minus 4 plus 4, that is equal to minus 16. 5 divides minus 12 minus 3 minus 15 plus, that is R is equal to 3 greater than 0. Minus 12 is equal to 5 into minus 3 plus 3, that is equal to minus 15 plus 3 minus 12. The remainder is always greater than 0. If these two conditions are satisfied, then the division is true, otherwise false. If these two conditions are satisfied, then by division of algorithm, the division is true. Here, modulo 5 divides A into B, gives the remainder. A into B modulo 5 is the same as remainder, that is R obtained dividing A into B by modulo 5. Here, construct the composition table or multiplication table. The binary operation. The binary operation star. The binary operation star is the multiplication modulo. Multiplication modulo is the multiplication. The binary operation star is the multiplication modulo. Modulo 5 denoted by multiplication suffix 5. The binary operation star is the multiplication modulo. A star B is equal to A into B modulo 5. The binary operation star is the multiplication modulo 5 denoted by multiplications 5. We have to construct the composition table or multiplication table for the binary operation star. Here the binary operation is the multiplication modulo, which is denoted by multiplication 5, suffix 5. Composition table. Or multiplication modulo 5 table. Multiplication modulo 5 table. Composition table or multiplication modulo 5 table. Multiplication modulo. Multiplication 5, suffix 5. The binary operation is the multiplication modulo 5 denoted by multiplication 5. 0, 1, 2, 3 and 4. The binary operation star defined on set of 0, 1, 2, 3, 4. 0, 1, 2, 3 and 4. 0 into 0, that is equal to 0. 5 divides 0 gives the remainder 0. 0 into 1, that is equal to 0. 5 divides 0 gives 0. 0 into 2, that is 0. 5 divides 0 gives the remainder 0. 0 into 3, 0. 5 divides 0 gives 0. Similarly, it is 0. 0 into 4, that is equal to 0. 5 divides 0 gives the remainder 0. 1 into 0, that is 0. 5 divides 0 gives the remainder 0. 1 into 1, that is 1. 5 divides 1. 5 divides 1. 5 divides 1. R is equal to 1, greater than 0. That is 1. Similarly, 1 into 2. 5 divides 2 gives the remainder 2. 5, 1 into 3, that is 3. 5 divides 3, 3 gives the remainder 3. 1 into 4, that is 4. 5 divides 4 gives the remainder, that is 4. 2 into 0, that is 0. 5 divides 0, it is 0. 2 into 1, that is equal to 2. 5 divides 2 gives the remainder 2. 2 into 2, that is 4. 5 divides 4 gives the remainder, that is 4. 2 into 3, that is equal to 6. 5 divides 6 gives the remainder 1. 2 into 4, that is 8. 5 divides 8 gives the remainder 3. 3 into 0, that is 0. 5 divides 0 gives 0. 3 into 1, that is equal to 3. 5 divides 3 gives 3. 3 into 2, that is equal to 6. 5 divides 6 gives the remainder 1. 3 into 3, that is equal to 9. 5 divides 9 gives the remainder 4. 3 into 4, that is equal to 12. 5 divides 12 gives the remainder 2. 4 into 0, that is equal to 0. 5 divides 0 gives 0. 4 into 1 equal to 4. 5 divides 4 gives the remainder 4. 4 into 2, 8. 5 divides 8 gives the remainder 3. 4 into 3, that is 12. 5 divides 12 gives the remainder 2. 4 into 4, that is 16. 5 divides 16 gives the remainder 1. Since A into B modulo 5 implies this, or which is same as remainder, that is R, obtained dividing A into B by modulo 5. Clear? Clear? Okay. The composition table. The composition table shows star is a binary operation. On set of 0, 1, 2, 3 and 4. Since for all AB belongs to set of 0, 1, 2, 3, 4 implies A star B belongs to set of 0, 1, 2, 3 and 4. The composition table shows star is a binary operation on this. Since for all AB belongs to set of 0, 1, 2, 3, 4 implies A star B belongs to set of 0, 1, 2, 3, 4. It is the definition of binary operation. Row 3. It is a row 3. Row 3. R3. Shortly it is written as R3. From the composition table, it is clear that row 3 denoted by R3 implies is equal to 1 is the identity element is the identity element in is the identity element on set of 0, 1, 2, 3, 4. Is the identity element, since 1 into 0 that is equal to 0, 5 divided 0 belongs to in this set. 1 into 1 that is equal to 1, 5 divided 1 gives 1 belongs to this set. And since E into A is equal to A for all A belongs to set of 0, 1, 2, 3, 4. E into A is equal to A for all A belongs to set of 0, 1, 2, 3, 4. Clear? It is the definition of the set A contains the identity element. Here the identity element is E. Row 3 implies this is equal to 1 is the identity element on this set. Since E into A is equal to A for all A belongs to which is same as E into A is equal to A which is same as A into E. Since E into A is equal to A which is equal to A into E. Clear? It is the definition of identity element in the set containing 0, 1, 2, 3, 4. So 1 is the identity element on this set. Clear? Next, we have to find out the inverse element of 2 and 4. 2 multiplied with 3 gives the identity element 1. So 3 is the inverse of 2. From the composition table, since E star A is equal to A for all A belongs to. It is the binary operation. E star A is equal to A for all A belongs to the set of 0, 1, 2, 3, 4. From the multiplication modulo table, modulo 5 table, we have the inverse of 2. 2 inverse is equal to 3. And the inverse of 4 and inverse of 4 is equal to 4. Since 2 into 3 is equal to 6, 5 divided 6 gives the identity element E. Since 2 star 3 is equal to 2 into 3 mod of 5 is equal to 1 is equal to the identity element. 4 into 4 star 4 is equal to 4 into 4 modulo 5 gives the identity element 1. is equal to E. In general, A into B, A star B is equal to E in general. In general, A star B is equal to E B star A. B is equal to A inverse. It is the definition of A star B is equal to E, then B is equal to the inverse of A. Clear? The composition table shows star is a binary operation on this. Since for all A B belongs to this, A star B is equal to this. Row 3 implies E is equal to 1 is the identity element on this set. Since E into A, E star A is equal to A, E star A is equal to A for all A belongs to set of 0, 1, 2, 3, 4. It is clear from the row 3. 1 into 0 is equal to 0 belongs to this set. 1 into 1 into 1 equal to 1, 5 divides 1 gives 1. All elements in row 3 belongs to this set. Clear? From the multiplication modular 5 table, we have 2 inverse is equal to 3. Since 2 into 3 that is equal to 6, 5, 2 into 3 is equal to 6, 5 divided 6 is equal to 1 is the identity element. 2 into 3 that is equal to 2 into 3 modulo 5 which gives the, that is 6, 5 divided 6 gives the remainder 1 that is the identity element. A star B is equal to E which is equal to B star A where B is the inverse of A. 4 into 4 that is equal to 16. 5 divides 16 gives the remainder 1 which satisfies the definition of inverse. So 2 inverse is equal to 3 and 4 inverse is equal to 4. Clear? Are you clear? Okay, note down. Next question. Elements of mathematics, page number 30, exercise 1C. Question number 3. In case star is a binary operation, test whether the following questions is associative. First bit, second bit commutative, third bit existence of identity and inverse element for any element of the respective set exist. A star B is equal to A plus B minus AB in set of a real number minus set of a 1. First we have to test star is a binary operation or not. Solution. For all A and B belongs to set of a real number minus set of a 1. That means set of all real numbers without 1. A plus B implies A plus B minus AB belongs to R minus set of 1. It is true for any real number without 1, which implies A star B. Since A star B is equal to A plus B minus AB in R minus set of 1 belongs to set of real number minus set of 1. For all AB belongs to R minus set of 1, that implies A star B belongs to R minus set of 1. Therefore, star is a binary operation in R minus set of 1. Set of real numbers without 1. In case star is a binary, here star is a binary operation. Next, we have to test the binary operation is associative or not. Test for associative. Test for associative. For all ABC, A and B and C belongs to R minus set of 1. A star B bracket star C. A star B is equal to A plus B minus AB. Star C. It is taken as A, it is B, which is equal to A plus B plus C. This plus this minus AB. This into this, that is equal to minus A minus BC plus ABC. It is taken as A, it is B, A plus B, that means A plus B minus AB plus C. Minus AB, it is taken as A, it is B. So A plus B plus C minus AB minus CA minus BC plus AB. It is taken as A, it is taken as B. A star B is equal to A plus B minus AB. A star B star C, which is same as A star B star C implies B plus C minus BC. Since A star B is equal to A plus B minus AB, it is A, it is B, which is same as it is A, it is B, A plus B plus C minus BC minus of AB minus of AC plus of ABC implies A star B bracket star C is same as A star B star C bracket implies A star B star C is equal to A star B star C. This is same as this. Therefore, the binary operation star is associative. The binary operation star is associative. Clear? Since A star B bracket star C is equal to A star bracket B star C. If this condition is satisfied, the binary operation star is associative. Second bit, it is the first bit. The first condition is satisfied. Second condition, that is commutative. Star is commutative or not. The binary operation star is commutative or not. For all A and B belongs to R minus set of 1 implies A star B is equal to A plus B minus AB and B star A is equal to B plus A minus B. A and B are the real numbers without 1. Real numbers are commutative and with respect to addition and multiplication, which is same as real numbers are commutative with respect to addition and multiplication. So we can write it A plus B minus AB, which is equal to B star, which is equal to A star B. A star B implies A star B is equal to B star A for all AB belongs to R minus set of 1. R minus set of 1. Therefore, since A star B is equal to B star A, for all A and B belongs to R minus set of 1, implies the binary operation is commutative. Therefore, the binary operation star is commutative. Clear? Since A star B is equal to B star A, the binary operation star is commutative. Third bit, existence of identity element in R minus set of 1. Existence of identity element in the set R minus set of 1. It is exist or not. Let E be the E possible. Let E possible. Let E possible. Let E be the identity element in set of real numbers minus set of 1. All real numbers, E possible, let E be the identity element in R minus set of 1. Let by definition A star E is equal to A for all A belongs to R minus set of 1. If possible, let E be the identity element in R minus set of 1. By definition, A star E is equal to A for all A belongs to R minus set of 1. It is the definition of identity, which implies it is A, it is B. A plus E minus AE is equal to A. A star B is equal to A plus B minus AB. A is taken, it is A, it is B. So A plus B minus AE is equal to A. For all A belongs to R minus set of 1, which is A cancel, E minus AE is equal to 0, which implies E 1 minus A is equal to 0, which implies E is equal to 0. Since 1 minus A not equal to 0, since 1 minus A, that is A not equal to, A is any real number but not equal to 1. A 1 minus A not equal to 0. That is A not equal to 1. A is any real number without 1. Therefore, the identity element in R minus set of G1 is 0. The identity element in R minus set of 1 is 0. That means the identity element is exist. Identity element is exist, implies is exist in R. Therefore, the identity element in R minus set of 1 is 0. Last, inverse element for any element of the respective set. Inverse element of an element A belongs to R minus set of 1. Inverse element of an element that is A belongs to R minus set of 1. The inverse of A is exist or not. The inverse of A is exist or not in R minus set of 1. If possible, let B be the inverse of A. By definition, A star B is equal to E, which is equal to B star A. A star B. What is A star B? A plus B minus AB. What is E? E is the identity element which is found out, that is E is equal to 0, which implies A plus B into 1 minus A is equal to 0, which implies B into A minus 1 is equal to A. B into A minus 1 is equal to minus cancel, which implies B is equal to A divided by A minus 1. A star B, it is the definition of inverse. A star B is equal to E, which is equal to B star A, which implies this A plus B minus A B equal to 0. A, B taking common, 1 minus A equal to 0. B into A minus 1, minus B into A minus 1 is equal to minus A, minus minus cancel. So B is equal to A divided by A minus 1 is exists in R minus set of 1. Since A not equal to 1. Clear? If A is equal to 1, B does not exist, but it is exists since A not equal to 1. Therefore, B is equal to A inverse is equal to A divided by A minus 1. Inverse of A is equal to B. That means the inverse is G, that is inverse is exist. Inverse is exist. Inverse is exist in R minus set of 1. A is an element in R minus set of 1. B is the inverse of A, whose value is A divided by A minus 1. Where A is an element in R minus, that is inverse of A is exist. Inverse of A is exist. Where A belongs to R minus set of 1. Are you clear? Are you clear? Okay, note down. Next, question number 3. In case star is a binary operation, test whether the following question is associative, commutative, existence of identity, and inverse element for any element of the respective set exists. The function is defined by, that is A star B is equal to GCD of A and B on N. First we have to show star is a binary operation or not. Solution. For all AB belongs to capital N implies GCD of A and B belongs to N is true. Since A and B belongs to N, GCD of, that means greatest common divisor of A and B, greatest common divisor of A and B must be belongs to N, implies A star B belongs to N. For all AB belongs to N, A star B belongs to N, it satisfies the definition of binary operation. Therefore, star is a binary operation on N. Clear? GCD of O, that means greatest common divisor of A and B must belongs to capital N. Since A and B belongs to N. GCD of A and B is same as A star B. For all AB belongs to N, that implies A star B belongs to N. Therefore, star is a binary operation on N. Second, we have to test the binary operation star is associative or not. Associative. For all A, B and C belongs to N, A star B bracket star C is equal to A star bracket B star C is true for all ABC belongs to N. This is same as this. For example, A is equal to 5, B is equal to 3 and C is equal to 2. A star B bracket star C is equal to 5 star 3 bracket star 2 5 star 3. That means GCD of 5 and 3 is 1 star 2. That means GCD of 1 and 2, greatest common divisor of 1 and 2 is 1. A star bracket B star C. A means that is 5 star 3 star 2. GCD of 3 and 2 is 1. And GCD of 5 and 1 is equal to 1. So A star B star C is equal to 1. A star B star C is also 1. So A star B bracket star C is equal to A star bracket B star C. Therefore, the binary operation star is associative on A. Clear? The binary operation star satisfies the definition of associative. So star is a binary operation on N. Test for commutative. A star B is equal to B star A for all AB belongs to capital N. GCD of A and B is same as, that is GCD of A and B is same as GCD of B and A. GCD of A and B is same as, that means greatest common divisor of A and B is same as greatest common divisor of B and C. Is it true? Therefore, star is commutative on N. The binary operation star is commutative on N. Clear? Since A star B is equal to B star A. Next, we will test existence of identity element in N. Third, it is first associative is first, commutative is second. Existence of identity element of identity element on N. The identity element in N is exist or not. If possible, let E be the identity element in N. If possible, let E be the identity element in N. By definition, A star E is equal to A, which is equal to E star A. For all A belongs to capital N. If possible, let E be the identity element in N. By definition, A star E is equal to A, which is equal to E star A, which implies GCD of A and E is equal to A. Is not true always. Since GCD, greatest common divisor of A and E is equal to A. Suppose A is taken as 2 and E is taken as 1. GCD of 2 and 1 is not equal to 2, that is 1. Is not equal to A is taken as 2, E is taken as 1. GCD of 2 and 1 is 1, which is not equal to 2. GCD of 3, 2. A is taken as 3, E is taken as suppose 2, is not equal to 3. Since GCD of 3 and 2, that means the greatest common divisor of 3 and 2 is 1, not equal to 3. Clear? Therefore, the identity element is E is not exist in N. Clear? The identity element is not exist in N. Clear? Okay. Last, inverse element. Inverse element of an element in N. The inverse element of an element in N in existence of existence of inverse element of an element in N. Existence of inverse element of an element in N. Since the identity element is not exist in N implies the inverse of one element in N is not exist. Since by definition A star A inverse is equal to E, which is the same as A inverse star A. For all A belongs to capital A. Since the identity element is not exist in N, implies the inverse of an element in N is not exist. Since it does not satisfy the definition of inverse, A star A inverse is equal to E, but E is not exist. Since E is not exist, the inverse is not exist. We will test the inverse if the identity element in the given set is exist. Since the identity element is not exist in N, the inverse is not exist in N. The inverse of an element in N is not exist since the identity element is not exist in N. Clear? Clear? Are you clear? Okay. Note down. Next, given A star B is equal to A plus B mod 7 on set of 0, 1, 2, 3, 4, 5, 6. Given A star B is equal to A plus B mod 7 on set of 0, 1, 2, 3, 4, 5, 6. Solution. A star B is equal to A plus B mod 7 on set of 0, 1, 2, 3, 4, 5 and 6. What is the meaning of A plus B mod 7? What is the meaning of A plus B mod 7? It implies remainder, that is R, obtained dividing A plus B by 7. A plus B mod 7 represent remainder, that is R, obtained dividing A plus B by mod 7. The operation star is equal to is called addition modulo 7 denoted by addition modulo 7 denoted by addition 7 modulo 7. It is denoted by symbol of addition 7 and read as addition modulo 7. The operation star is called addition modulo 7 denoted by addition suffix 7. Composition table or addition modulo 7. What is the composition table? That is addition modulo 7. Addition suffix 7. Zero, 1, 2, 3, 4, 5 and 6. 0, 1, 2, 3, 4, 5 and 6. 0 plus 0, that is equal to 0. 0 divides 0 plus 0, that is equal to 0. 7 divides remainder, that is r obtained dividing a plus b by modulo 7. 0 plus 0, that is equal to 0. 7 divides 0 gives the remainder 0. 0 plus 1, that is equal to 1. 7 divides 1 gives the remainder 1. 0 plus 2, that is equal to 2. 7 divides 2 gives the remainder 2. Similarly, it is 3, it is 4, it is 5. 0 plus 6, that is equal to 6. 7 divides 6 is the 6 gives the remainder 6. 1 plus 0, that is 1. 7 divides 1 gives the remainder 1. 1 plus 1, that is 2. 7 divides 2 gives the remainder 2. Similarly, it is 3, it is 4, it is 5, it is 6. 1 plus 6, that is equal to 7. 7 divides 7 gives the remainder 0. 2 plus 0, that is equal to 2. 7 divides 2 gives the remainder 2. Similarly, it is 3, it is 4, it is 5, it is 6. 2 plus 5, that is 7. 7 divides 7, that is equal to 0. It is 1. Similarly, it is 3, it is 4, it is 5, it is 6. And it is 0, 1, 2. That is 4, it is 5, it is 6. And it is 0, it is 1, it is 2, it is 3. 4 plus 6, that is equal to 10. 7 divides 10 gives the remainder 3. It is 5, it is 6, it is 0, 1, 2, 3, 4. It is 6, it is 7, that is 0, 1, 2, 3, 4 and 5. Since 6 plus 6, that is equal to 12, 7 divides 12 gives the remainder 5. Clear? A plus B modulo 7. The binary operation is called addition modulo 7, which gives the result. The composition table shows star or addition modulo 7 is a binary operation. The composition table, this composition table shows star or addition modulo 7 is a binary operation. Since for all AB belongs to set of 0, 1, 2, 3, 4, 5, 6 implies A star B belongs to set of 0, 1, 2, 3, 4, 5, 6. This composition table 0 plus 0 divide equal to 0 divided by 7 gives 0. That means for all AB belongs to this set, A star B belongs to this star or addition modulo 7 represent a binary operation. Clear? The composition table shows star is a binary operation. Since AB belongs to this set, A star B is also belongs to this. All elements belongs to this set. Next we have to test associative. Star or addition modulo 7 satisfies the properties of associative or not. For all A, B and C belongs to set of 0, 1, 2, 3, 4, 5, 6. For all ABC belongs to this set, A star B bracket star C is equal to A star B star C. Is true always. Is true always. It is clear from the composition table. For example 2 star 3 star 5 is equal to 2 plus 3 that is equal to 5. 2 plus 3 that is equal to 5. 5, 7 divides 5 gives 5. 5 star 5. 2 plus 3 that is equal to 5. 7 divides 5 gives the remainder 5. 5 star 5. That means 5 plus 5 that is 10. 7 divides 10 gives the remainder 3. Which is same as? Which is same as 2 star 2 star 3 star 5. Since 3 plus 5 that is equal to 3 plus 5 that is equal to 8, 7 divides 8 gives the remainder 1. So it is 2 star 2 star 1. 2 star 1 means 2 plus 1, that is equal to 3. 7 divides 3 gives you the remainder, that is equal to 3. 2 star 3 bracket star 5 is the same as 2 star bracket 3 star 7. It is the example of associative. Therefore, so star the binary operation star is associative. So the binary operation star is associative. Clear? Since A star B bracket is star C is equal to A star bracket B star C. This is the example of the above. Next, commutative. The binary operation star satisfies the commutative properties or not. For all AB, A and B belongs to set of 0, 1, 2, 3, 4, 5, 6. A star B is the same as B star A. A star B is equal to B star A is true always. True always. For example, four star 6. That means 4 plus 6, that is 10. 4 plus 6, that is equal to 10. 7 divides 10 gives the remainder 3, which is same as 6 star 4. 6 plus 4, that is equal to 10. 7 divides 10 gives the remainder 3. 4 star 6 is equal to 6 star 4. Therefore, the binary operation star is commutative. The binary operation star is commutative. Next, existence of identity element. Insert this. Existence of identity element in existence of identity element in set of 0, 1, 2, 3, 4, 5 and 6. The identity element is exist or not. It is row 1, first row. It is second row. It is third row. It is fourth row. Fifth row. Sixth row. Seventh row. And 1, 2, 3, 4, 5, 6, 7 into 80. Row 2 implies Row 2 implies row 2 denoted by R2 implies 0 is the identity element. Row 2 implies 0 is the identity element in set of 0, 1, 2, 3, 4, 5 and 6. Since for all A belongs to set of 0, 1, 2, 3, 4, 5 and 6 implies A star E is equal to A, which is same as E star. A star E is equal to A. These are the elements, represent the elements of A, and 0 is the identity element. These are the elements of the set. These are the elements of the given set which represent A. 0 is the identity element. 0 plus 0, that is equal to 0. 7 divides 0 gives 0. 0 plus 1, that is equal to 1. 7 divides 1 gives 1. This row is same as this row. A star E is equal to A. E is equal to E star A. Implies where E is equal to 0. Where E equal to 0, row 2 implies 0 is the identity element in this set. Since for all A belongs to this A star E, A means 0, 1, 2, 3, 4, E is equal to 0. If E equal to 0, A is 0. 0 plus 0, that is equal to 0. 7 divides 0 gives 0, which is equal to 0. If A is equal to 1, E is equal to 0. 1 plus 0, that is equal to 1. 7 divides 1 gives 1. Is always true. So E equal to 0 is the identity element in sets containing these elements. Next, existence of inverse. Next, existence of inverse. Existence of inverse of an element. Existence of inverse of an element in set of 0, 1, 2, 3, 4, 5 and 6. Existence of inverse of an element. From the composition table, it implies 0 is the identity element. 0 plus 0, that means 0 star 0 gives 0. The composition table shows inverse of 0. The composition table shows inverse of 0 is equal to 0. Since 0 plus 0, that is 0. 7 divides 0 gives 0. Inverse of 1. Inverse of 1. 1 plus 6. 1 plus 6, that is 7. 7 divides 7 gives the remainder 0. So, inverse of 6. Inverse of 1 is equal to 6. Inverse of 6 is equal to 1. Inverse of 2. Inverse of 2. Inverse of 2 is 5. Inverse of 2 is 5. And inverse of 5 is also 2. Since 2 plus 5 equal to 7, 2 plus 5 is equal to 7, 7 divides 7 gives the identity element, that is 0. Inverse of 4 is 3. 4 plus 3, that is equal to 7, 7 divides 7 gives the remainder, that is 0, which is the identity element. Inverse of 3 is equal to 4 and inverse of 4 is equal to 3. Since A star, A inverse is equal to E, which is equal to A star, A inverse star E. The above results implies A star, A inverse is equal to E, where E is equal to 0. That means 0 plus 0, inverse of 0 is 0. Inverse of 0 is 0. A is 0 and its inverse is also 0. 0 plus 0, that is equal to 0. 7 divides 0 gives the identity element 0. 1 plus 6, that is equal to 7. 7 divides 7 gives the identity element 0. Clear? Last, 3 plus 7 is equal to 7. 3 plus 4 is equal to 7. 7 divides 7 gives the identity element, that is equal to 0. So, the composition table shows inverse of 3 is equal to 4 and inverse of 4 is also 3. Inverse of 3, that is 4. Inverse of 4 is equal to 3. Since 4 plus 3, 4 plus 3 is equal to 7. 7 divides 7 gives the remainder, R is equal to 0. So, inverse of 0 is equal to 0, inverse of 1 is equal to 6, inverse of 6 is equal to 1, inverse of 2 is equal to 5, inverse of 5 is equal to 2, inverse of 3 is equal to 4, inverse of 4 is equal to 3. Since the above results implies A star, A inverse is equal to E, where E is equal to 0. Clear? Clear? Every element in this set has the inverse. Inverse of 0 is 0, inverse of 1 is equal to 1, inverse of 2 is equal to 5, inverse of 3 is 4, inverse of 4 is equal to 3, inverse of 5 is equal to 2, inverse of 6 is equal to 1. All elements in this set has the inverse, and the 0 is equal to E is equal to 0 is the identity element. E equal to 0 is the identity element in this set. Clear? Are you clear? Okay, note down.